Hey, good day. So let's have another example for the portal method. Okay, for example, we have this frame loaded as shown, and we are to analyze this frame using the approximate method, portal method. So first thing to do, or on the first assumption, we are to name the points of inflections. These are the points middle or mid-height for columns and mid-span for beams. So let's say we have this points A, B, C. Then for beam DE, it is point D. For beam EF, it is point E. Then for the second level, this is, let's say, point F, a point G, then a point H. So these are the points of inflection. So again, at the point of inflection, the magnitude of the moment is equal to 0. So we are to start the analysis on the second level. So we are considering the upper half of the second level, starting from the points of inflection. So based on the first assumption of, or the assumption of the portal method, we have the magnitude of the shear for the columns for exterior will be, let's say, V. Twice of that shear will be the magnitude of the shear for interior columns. So for this case, what will be the magnitude of the shear for these 2 points? Let's say this is the point of inflection, this is point F, and this is, I think this is point G. So we have the magnitude of the shear. Since both are exterior columns, we don't have an interior column on the second level. This is shear V and let's say shear V. So we can directly compute for the magnitude of the shear of the columns on the second level. Basically, this is by summation of forces, horizontal equal to 0, assuming to the right forces to be positive. So that is, basically we have 80, this is 80, minus B is equal to 0. So this is twice of B is now equal to 80, divided by 2. So we have the magnitude of the shear for both columns on the second level is equal to, simply equal to 40 kilonewtons. So this is 40 kilonewtons. This is 40 kilonewtons. That is for the shear force for both columns on the second level. Now we are considering the first level. We are to start or separate the part of the frame starting on these inflection points of the columns on the first level. So we have this points of inflection. This is, I think this is point A, point B, then this is point C. So using the assumption of portal method, we have the magnitude of the shear for exterior columns will be V. This is for our 2 exterior columns, and the magnitude of the shear for interior columns will be equal to twice of B. So we have to do is to compute for the magnitude of the shear. Let's say for the second level, this is B sub 2. And for the first level, we name them as, let's say, B sub 1. By summation of forces, this is by summation of forces horizontal equal to 0, assuming to the right forces to be positive. So that is, we have 80 kilonewtons plus 100 kilonewtons minus B1 minus twice of B1 minus B sub 1 is equal to 0. So we having, this is 4 of B1 is equal to 180. And then dividing both sides of the equation by 4, we have the magnitude of the shear for exterior columns on the first level. That is 180 divided by 4. So it's equal to 45 kilonewtons. So this is, for exterior columns, this is 45 kilonewtons. 45 kilonewtons. So what is twice of 45? Twice of 45 is equal to 90 kilonewtons. So after computing for the shear force for all levels for all columns, we may now analyze the entire frame. So we are to draw the free body diagram of the frame. So separating all joints from their points of inflection. So on the second level, Okay, we have this load acting at point G, 80 kilonewtons to the right. So we are able to compute for the shear for column DG. This is 40 kilonewtons. That is the shear force for all columns on the second level. This is 40 kilonewtons. So again, I'll be using green for shear. So when it comes to the distances, all we have to do is consider the mid-span of the beams and mid-height of the columns. So our beams are 8 meters long and all columns are 4 meters long. So if we are to consider their mid-length and mid-height, this is 4 meters and this is 2 meters. So we can now compute for the axial force. I'll be using red for axial force. The axial force for beam GH. So if we are to do the manual computation, that is basically 80 kilonewtons minus 40. The axial force for beam GH is equal to 40 kilonewtons. Now computing for the axial force for column DG. Let's say this is the axial force for column DG. So this is initially the point of inflection. This is point H. Okay, we may do the summation of moment about point H equal to 0, assuming clockwise moments to be positive. That is, we have 40 times 2 minus the axial force for column DG. This is multiplied by 4 is now equal to 0. So we have the axial force for column DG. 40 times 2 is 80 divided by 4. This is the same as the 20 kilonewtons. So axial force for column DG is 20 kilonewtons. Summation forces vertical, we can now have the magnitude of the shear force. The shear force for beam GH. So at joint G, we have only one vertical force so far. That is the 20 kilonewtons. So summation forces vertical, to be in equilibrium, the shear force for beam GH should be the same as 20 kilonewtons. Now checking for the equilibrium of joint G, what is 20 times 4? I'll be using blue for the moment. 20 times 4 is 80 kilonewton meter. What is 40 times 2? 40 times 2 is the same as the 80 kilonewton meter. So that is for joint G. Then at joint H, we are just to transfer the values considering the opposite direction of the forces. So this is 20 kilonewtons. This is 40 kilonewtons to the right, axial force for beam GH. Then for the shear, this time it should be 20 kilonewtons downward. So as you can see, 40 to the right, 40 to the left. So horizontally, it is in equilibrium. So for the vertical forces, this is for the axial force for column EH. Summation forces vertical, we have only one vertical force, that is the 20 kilonewtons. So we need 20 kilonewtons upward. If we are to check for the equilibrium, again, this is 4 meters and this is 2 meters. So 20 times 2 is the same as, that is 40 times 2, this is the same as 80. Then 40 times 2 is the same as 80 kilonewton meter. So joint H is in equilibrium. So we proceed on the first level. So what are the shear force for all columns? We are to place them. So for column AD, the magnitude of the shear is 45. The same with for column CF, this is also equal to 45 kilonewtons. And the shear for the interior column is equal to 90 kilonewtons. Now, we are to transfer the values from the second level. So we will be having this time an axial force. It should be upward this time. This is 20 kilonewtons upward. Then for the shear, this time, this is 40 kilonewtons to the right. So at joint D, we have the lateral load. This is the 100 kilonewtons as given. Okay, so based on what is available or what are the available values at joint D, we can now compute for Okay, the axial force. Okay, first thing to solve at joint D. This is the axial force for beam DE. So all we have to do is summation of forces, horizontal. So we have, to the right forces is 100 plus 40, that is the 100 kilonewtons and the 40 kilonewtons. Then minus this 45 kilonewtons to the left, minus 45 is equal to 95. So we have an axial force is equal to 95 kilonewtons. That is for beam DE. Okay, then next. Again, when it comes to dimension, this is 2 meters. This is 4 meters. This is 2 meters. We can now compute for the axial force. This is for the axial force for column AD. So initially, this point of inflection is the point D. We may do summation moments about that point. So doing the summation of moments about the point of inflection D equal to 0, assuming clockwise moments to be positive. So we have that as 45 times 2 meters plus, this is 20 times 4, then plus, this is 40 times 2 minus, this is the axial force for column AD multiplied by 4 equal to 0. So we will be having the axial force for column AD. That is, we have 45 times 2, plus the 20 times 4, plus 40 times 2. That is equal to 250 to be divided by 4. So we have that value as equal to 62.5 kilonewtons. So we have the axial force for column AD is now equal to 62.5 62.5. This is 62.5 kilonewtons. So, okay, we next to compute is the shear force. This is the shear force for beam DE. I'll be assuming it is upward. The shear force for beam DE. All you have to do is do the summation of forces vertical. Okay. So what are the vertical forces at joint D? So we have that as 20 minus 62.5, the axial force for column AD. So it is negative 42.5. So to be in equilibrium, we need it upwards. That is, the shear force for beam DE is now equal to 42.5, 42.5 upward. Okay, so I think all forces are now complete at joint D. Let us check the equilibrium. So when it comes to the moment, this is 40 times 2. That is the same as 80 kilonewton meter. This 45, the 45 kilonewtons times 2 is equal to 90 kilonewton meter. Then what is the moment caused by the shear force, the 42.5 about joint D? That is 42.5 multiplied by 4. That is equal to 100. This is equal to 170. If we are to check the equilibrium, the summation of moments about joint D should be equal to 0. So we have two clockwise moments, that is the 90 plus 80 minus the counterclockwise, 170. And that is 0. Therefore, joint D is in equilibrium. The next is at base A, transferring the values considering the opposite direction for forces. This is now upward, 62.5 kilonewtons. So therefore, the vertical reaction at base A should be equal to 62.5 kilonewtons downward. Then for the shear, this is 45 kilonewtons to the right. So the base shear at A should be equal to 45 kilonewtons to the left. Then for the moments, this is 45. Again, this is 2 meters. 45 times 2 is 90. This is 90 kilonewton meters. So therefore, the moment reaction at the base A, is 90 kilonewton meter counterclockwise. That is for column AD. So we proceed to joint E. Alright, so transferring the values. This is now 20 kilonewtons downward. This is 95 kilonewtons to the right. That's 95. Then for the shear, this time it should be downward. This is 42.5 kilonewtons downward. Okay. Then the shear for beam EH should this time this is 40 kilonewtons to the right. So first thing to solve is the axial force. This is the axial force for column for beam EF. So axial force for beam EF. So all we have to do is do the summation of forces horizontal at joint E. We have 95. Okay, this 95, then this 40 less this 90. 95 plus 40 minus 90. So the axial force for beam EF is now equal to 45 kilonewtons to the left. Then, okay, we are now to compute for the axial force. This is the axial force for column, this column is BE. That is column BE. So I'll be assuming it is upward. The axial force for column BE. So when it comes to the distances, this is 2 meters, 4 meters. This is the same as 2 meters. This is 4 meters. So this point of inflection, this is the point of inflection, point E. So I'll be doing summation of moment about this point of inflection, the point E. We have the summation of moments about the point of inflection, point E, equal to 0, assuming clockwise moments to be positive. So what are the positive moments? That is the axial force for column BE. This is multiplied by 4 plus 90. This is multiplied by 2. Then plus 40. This is multiplied by 2. Minus 20. This is multiplied by 4. Then minus 42.5 multiplied by 8 equal to 0. So computing for the axial force for column BE. As we have that as 90 times 2, plus, this is 40 multiplied by 2, and then minus the 20 times 4, then minus the 42.5, that is 8 meters away. This multiplied by 8. It's negative 160 to be divided by, to be transposed, that will be positive to be divided by 4. So we have the axial force is 40 kilonewtons. So this is 40 kilonewtons. So correct assumption, this is equal to 40 kilonewtons upward. So if we are to do summation forces vertical, we'll be having the shear force. This is the shear force for beam EF. So what is that value? So summation of forces vertical, we have 42.5. That is the upward force. 40 minus 42.5 minus 20. That is negative 22.5 transpose, which means that will be positive. Correct assumption? 22.5 kilonewtons upward. Okay, then we are now to check the equilibrium about joint E. So for the equilibrium, what are the moments? 42.5 times 4, we have this earlier, that is the same as 170. This is 40 times 2, we have that also from the second level, that is the same as the 80 kilonewton meter. This is 90 times 2, 90 times 2 is equal to 100. This is 180, 180 kilonewton meter. Then 22.5, what is 22.5 times 4? 22.5 times 4 is equal to 90. So if you are to check the equilibrium, the summation of moments about joint E should be equal to 0. So we have 2 clockwise, that is 180 plus 80. Counterclockwise, 170. Okay, then the 90. And it is equal to 0, which means joint E is in equilibrium. Okay, so dito na tayo sa base B. Okay, so again, transferring the values. So this is, okay, we have 40 kilonewtons this time, downward. So the vertical reaction at B should be, it should be 40 kilonewtons upward. Then for the shear, this is, we have 90 kilonewtons to the left. Then the base shear at B should be 90 kilonewtons to 90 kilonewtons to the right. The base shear at B should be 90 kilonewtons to the left. Then for the moments, so this is 90 times, again, this is 2 meters. 90 times 2 is 180. And the moment reaction at the base B should be, it should be 180 kilonewtons, kilonewton meter. Okay, that is for base B. Then for the last column, this is column CF. So the axial force for beam EF, this time, this is 45 kilonewtons to the right. Then the shear, this is 22.5 kilonewtons downward. So for equilibrium, as you can see, if you are to check the forces, the horizontal forces, there is 45 kilonewtons to the right and 45 kilonewtons to the left. Then the axial force for column CF, you have the axial force for column CF is the same as this vertical force, 22.5. Then for the moments, this distance is 4 meters. This is 2 meters. So that is 22.5 times 4. We have that from joint E as 90. Then 45, this is 45 kilonewtons times 2 is the same as 90 kilonewton meter. Then at base C, this axial force is 22.5 kilonewtons downward. Then the vertical reaction should be equal to 22.5 kilonewtons. Then if we have to check the equilibrium, vertical equilibrium, as you can see, we have this 62.5 downward, 40 and 22.5 upwards. So in equilibrium, that is 62.5. Just one way to check, minus 40 minus 22.5. And that is equal to 0. Then for the shear, this is 45 kilonewtons to the right. So the base shear at C is 45 kilonewtons to the left. Then the moment, 45 times 2 is 90 kilonewton meter. So the moment reaction at C, at the base, should be equal to 90 kilonewton meter counterclockwise. So this is the complete analysis of the frame using Portal method.